The door is closed, so we can start. And our first speaker is Michael, and he will be presenting Cachet, a domain-specific language for trustworthy just-in-time compilers. The floor is yours.
All right. Oh dear. Okay, is it working now?
Yes.
Okay, cool. Hi, I'm Michael Smith. I'm from UC San Diego, and we've been working on applying verification to make just-in-time compilers safer. So JITs are interesting because they deal with taking code that's often high level and often coming from sources that are untrusted or even directly adversarial, and turning it into fast, low-level machine code, which is further patched and repatched and re-optimized as the program runs. And they have to do all this compilation in a very tight time budget because ultimately JIT compilation is a performance optimization, and the more time you spend in the compile step, the less time you're spending reaping its benefits. What all this means is lots of complicated security invariants because machine code, and lots of clever tricks that can easily mess all those invariants up if we get them wrong. In particular, we're interested in verifying SpiderMonkey, Firefox's high-performance JavaScript JIT engine. In order to be a competitive JavaScript engine, SpiderMonkey is necessarily a very complicated beast with multiple interlocking components and systems. That's too much to tackle all at once, so we're breaking it down and tackling it component by component, applying verification techniques to improve confidence in each piece of the JIT as we go. We built a new language we're calling Cachet, specifically for the purpose of verified JIT implementation, which we've used for verifying things like range analysis, but today I'm here to talk to you about using Cachet to build a verified inline cache system. So the core problem that JavaScript engines have to deal with is that JS is an incredibly dynamic language. Basically, every expression you write introduces some kind of polymorphism. Everything from arithmetic to property accesses can have wildly different behaviors depending on the types of the values involved. And it would be too expensive and too slow to emit code that handles all possible cases for every expression. So instead, JS just use inline caching, where whenever one of these expressions is evaluated with types the engine hasn't seen there before, the engine first evaluates it in the slow path, figuring out what's going on with the types, and then generates a fast code stub to handle a specific situation. And then the JIT patches the original side of the expression with a jump to that new code stub so that future executions will take the fast path. Importantly, that means code stub needs to handle values of types that potentially hasn't seen before on those future executions. So let's zoom into one of these kinds of expressions, the object property access. In SpiderMonkey, this is a getProp operation. And what this actually does at runtime depends on what foo is and where bar is located on foo. Let's assume for simplicity that foo is just a simple plain JavaScript object with bar as its first property. So then in SpiderMonkey, foo will be laid out in memory using what's called a native object structure. Now the first 8 bytes of all objects in SpiderMonkey are a pointer to an immutable structure called a shape, which defines the kind and memory layout of the object. It's effectively a kind of type for objects. For native objects, the object memory layout will be followed after the shape pointer with a series of fixed slots, where property values are stored by index in line with the object's memory. The first value, which here is where the value of bar is stored. Now, how do we know that this value in the slot is bar? It's just got a 0 index. Well, if we follow the shape pointer, we can see that it notably has a dictionary of property keys, including bar, which is marked as being in slot 0 for objects with this shape. SpiderMonkey tries to share these shapes between all objects with the same layout and behavior, so checking foo's shape pointer implies the location of bar in its memory. Also relevant here is that shapes have a class pointer, which goes to another immutable structure, a class, which is a kind of an even more generic version of a shape. And in this case, what's relevant here is that the class of foo has a flag on it, which marks it as a native object, say a proxy or a DOM object or a cross-compartment wrapper or some other exotic JavaScript VM thing for which you could have a different memory layout and behavior entirely. So for this specific situation, how can we emit a code stub that can read bar from this foo fast? Well, what SpiderMonkey will do is it will generate this code stub in an intermediate representation called cache IR. And to read bar from this foo in cache IR, we can insert a load fixed slot result instruction, which says to load the value from the fixed slot, that's 8 bytes, into the input object's memory, into the output register. So this will work for this particular foo with this particular bar. But note that when this fast path code stub gets called again in the future, well, first off, foo is not even guaranteed to be an object. It could be a string or an integer. And if we treat it as an object pointer, well, type confusion is a huge source of security bugs in JavaScript JITs. So we need to preface this first with a guard that the value we're dealing with is actually an object. And if that's not the case, this guard instruction will bail out to the VM to fall back to the slow path. But even once we know that foo is an object, we still don't know that bar is going to be located in its first fixed slot. For example, the object could be empty, having no slots, in which case reading 8 bytes past its pointer is a read out of bounds. Or the object could be a proxy or a DOM wrapper or something else, or reading that location in its memory leaks some random bits of JIT internal stuff. So what's the fastest way we can do this check? Well, if you recall, that shape pointer on foo implies the layout of its properties, with bar in its first slot, and also implies that foo is a native object via the class. Therefore, because shapes and classes are immutable, we should be safe if we insert a check that the shape pointer on foo matches what we expect to be handling in this case. And once SpiderMonkey has emitted this program in Cachet, it lowers it down to macro assembler, or MASM for short, another SpiderMonkey internal IR at a lower level. So for example, guard2object in Cachet gets translated to MASM as a branch on the input value's type tag, which branches off to a failure bailout path if the tag doesn't match, followed by another MASM instruction that unboxes the object's pointer. And this MASM gets lowered down further to platform-specific assembly like x86, ARM, etc. So what does generating these Cachet programs look like in SpiderMonkey? Well, it's a big old C++ switch statement, which runs through every possible case and manually emits Cachet instructions to try and handle whatever a case matches. Critically, this code generator tries to emit the minimal set of guards, which makes stuff safe to run, so they'll be fast still. And that's all hand-rolled. It should be setting off alarm bells. What happens when we mess that up? Well, the C++ compiler, if we emit the guard shape clause, for example, it just says, I don't know, looks fine to me. And then the attacker quickly pwns our engine because they can now trick it into doing reads out of bounds or whatever. That's not ideal. We designed Cachet to try and do better than this, to provide a more principled foundation for building secure JITs. Now, we had 3 primary goals in mind when building Cachet. First, it needs to be practical for use by JIT engineers in the real world. Second, it should be composable, so that we can reap the benefits of verification as early as possible, without having to wait until we, say, port the entire engine into Cachet. And so that in the future, as we port more layers up and down the stack, we get compounding benefits from doing that. And thirdly, we need to be able to both express and check the invariants we want to ensure in a reasonable amount of verification time, so it can be integrated into a reasonable development iteration cycle for the JIT developers. So now to give an example of what I mean when I say practical for production JIT engineering, this is just scrolling through the commit history for the file that defines just the list of Cachet ops and the inputs and outputs they take. This file has had 528 revisions over the past 2.5 years. That's an average of a change every 2 days. And that's not even including the implementations of instructions. That's just their signatures. Takeaways from this are that first, having a huge separate manual proof is completely unviable. It'd be way too much work to keep that up to date with the rest of the code. And it would require engineers uniquely highly specialized in both JIT engineering and proof techniques to do even that. Instead, the invariants that we're checking should be in line with the implementation as much as possible. As someone who's worked on this area of the code base myself, I can tell you that SpiderMonkey developers are already used to peppering their code with various runtime asserts, but most of these get turned off for release builds because they're too slow to actually deploy to users. Being able to statically check assertions that get written along with the implementation, as well as actually being able to write assertions about the behavior of the code that our code is generating, that would be incredibly useful. Also, because the JIT code base, again, moves at such a high velocity, it'll be a non-starter to have like the one version of the JIT we verify and then the one we actually run be separate things. Keeping them in sync will be too much work and too error prone. Instead, for Cachet, we generate both the actual implementation that gets run in the browser, as well as the model that gets checked from the same code base. And we automate as much as verification as possible. So to serve this goal of practicality, we designed Cachet as a domain-specific language, purpose-built for JIT engineering. On the left here, you have the existing SpiderMonkey C++ implementation of the lowering of load fixed slot result from Cachet down to MASM. On the right, you have the equivalent Cachet code. And if you compare the two, you can see they have the same structure, but the Cachet code strips out a lot of the C++ line noise. Because building a compiler is a first-class part of the language, we have constructs explicitly designed for this. A first-class notion of declaring IRs and the ops to make them up, as well as lowerings between IRs, and emitting ops in those IRs at runtime with static emit statements. This makes it both easier for the JIT engineers to write natural compiler code, hiding much of the complexity they'd otherwise have to deal with, both in implementing the compiler and in setting up a correctness proof for the verifier. And also, this allows us to more easily verify the code they're giving us by forcing it into this specific structure that we can apply clever tricks to make verification tractable. At the same time, we still need C++ to be able to integrate it into Firefox and the rest of the JIT engine. So we take this input Cachet code and we generate C++ that looks pretty much the same as the code on the left, but with a bit more like tight boilerplate C++ stuff added to it. Now, Firefox is an enormous beast of an application. So we built Cachet so that you can port code piecemeal, pay-as-you-go style, and benefit from verification without having to write the whole JIT engine in Cachet. Calling out to external code is easy. You just declare the signature of the function you want to call on the Cachet side, and then you tie that up with a little binding code on the other side, most of which is auto-generated for you. You can leave the behavior of the function completely unspecified, or you can refine these function stubs with additional invariants about their behavior that the verifier can use to make your proof check out. For example, here we say there's something called a value in the JS engine. It's just some type. We don't know anything about it, but it's there. And then we say you can ask values for their type tags, and you can also convert them into objects. Then we further refine toObject with first the assertion that we must know for sure that the type of value is object before doing the conversion. And also with the assumption that if you take the unboxed object and you box it back into a value, you get the same tag value pointer that you started with. So once you lay out this information about the VM, the runtime, the rest of the world that you're dealing with. And then once you've got that, you can start building up your verified pipeline in layers that compose with each other. So you can start with, let's say, you write out your cache-ir to macroassembler lowering that takes in your cache-ir instructions and spits out more MASM instructions. On top of that, you can then layer your code that actually spits out cache-ir subcode and hook that up to your cache-ir to MASM lower. So now you have a cache-ir code generator down to MASM pass. On the bottom there, you can hook up a definition of your MASM interpreter, which talks to your VM runtime environment that you've defined. And now if you verify this whole thing end to end, you get an assurance that any code that your stub generator generates, first off, will not violate any invariant specified in your compiler. And then also any code, any of those programs that your code generator generates, once those programs are compiled to macroassembler, and once those programs are then run on the symbolic interpreter, they will never violate any of the invariants you specified in your rest of the world or in your model of the interpreter, the macroassembler running. You can also swap out pieces of this. So for example, you could take, instead of going from your code generator to a lowering to macroassembler, you could implement an interpreter directly for cache-ir that talks to the world directly. And in the future, we'd like to do some stuff about equivalence checking between, say, a cache-ir interpreter and a cache-ir to macroassembler lowering combined with an interpreter. You could also, and this is something we were doing already, is you could hook a fuzzer up to Firefox, and you could have Firefox dump out like real-world cache-ir stubs, then plug those stubs into your cache-ir to MASM lowering and plug that into the interpreter and get translation validation of those real stubs that you're seeing go through the browser. So to actually do the verification, we take the Cachet code and we compile it to Boogie, which is a language designed at Microsoft Research for essentially being a compiled target for languages of verification. We do some tricks, which I'll talk about in a little bit, to produce a specific Boogie program that's structured so that A, it will verify in a reasonable amount of time, and B, verifying it proves that whole pipeline correct. Oh, and we run the Boogie code through the Corral solver, also from Microsoft Research, which is specialized for assertion checking. It does. They have a great paper on reachability modulo theories, checking that effectively that any code is checking whether a code is reachable, and we use this to check that assertions will not be violated. So you can, in Cachet, you can encode the invariants of your JIT as effectively as assertions. So for example, we want to encode the property that objects can only be treated as native objects if their shape has a class flagged as native. So we can take the we can take the function for converting objects to native objects, and we can say, okay, we're going to grab the shape of the object. Then we grab the class of the object, and then we assert that the class has a native flag, and then only then are we allowed to convert the object to a native object. And so whenever your code generator generates a Cachet program that generates some MASM that tries to take an object and treat it as a native object, it will pass through here, and in order for that to fly, you will have to have something ensuring, say, a guard that ensures that the object's shapes class will have that native flag. In turn, we also want to encode that accesses to an object's fixed slots are within the bounds specified by the object shape. So what you can do here is we take the native object, we say it has some method get fixed slot. We say it has an effect where it reads the heap, so that if you call this multiple times, it may return different results. And we refine that definition of get fixed slot by saying, okay, whenever we're doing get fixed slot, we're going to grab the shape of the object. We're going to assert that the slot is within bounds. And then only if that's the case, then we're going to allow this to go through the actual get fixed slot method. So now here is a minimal version of what we showed before with the code generator just handling the native object fixed slot case in Cachet. And I've highlighted the emit statements emitting the same I forgot to highlight return from IC below, but it would emit the same program we saw before with the guard2 object followed by the guard shape followed by the load fixed slot result. But this time, unlike the previous case of C++, if we omit the, I should also point actually, this will, as written, it will check out because as you can see in the code generator, we're checking that the value is an object. What was it doing? Oh yeah. For example, the guard shape will check out because sorry, 1 second. Okay, I'm rebooted. When we are generating the load fixed slot instruction, we only emit that load fixed slot instruction after we've emitted a guard instruction using a shape that we have already checked implies that that shape has that fixed slot. There we go. Got it, eventually. So anyway, if we emit that guard shape instruction, now there is nothing protecting our load. Like we have, okay, the code generator checked that the shape has the fixed slot. But remember that this program that it's generating will be exposed to other inputs beyond the ones that the code generator is looking at right now after the code stub has been emitted and attached to the program. Without the presence of this guard shape instruction, there's nothing to say that the future inputs coming in will have the same shape, and so we don't have that implication that it is safe to read that slot from that object. So what happens if we omit this in contrast with the C++ version? Well, if this will play, yes, great. This ends up plugging it through the corral verifier, and you get this very long execution trace that ultimately boils down to, if you could kind of look at the end here, I think I have another slide, which, yes. Ultimately, this is the trace of a possible program execution through your code generator and then through its generated code in your macro assembler interpreter. That ultimately points a finger at saying that I cannot prove this assertion that the class of your object is a native object when I try to convert it to a native object. Now, this is a big, long trace thing to look at. This is this project is like a work in progress. We're in the evaluation stage, but we're planning on producing tools to making these more interpretable, more readable. But for now, you can just ask ChatGPT what it means, and it will tell you. You can even ask it what it means in terms of spider monkey, and it will tell you. So stopgap for now. In order to make the Boogie programs that we generate tractable, effectively, when we're verifying the whole pipeline end-to-end thing, what we're verifying is the version of the code generator that spits out the program in Cachet symbolically. Then we have the macro assembler code generator go over that and spit out the macro assembler program symbolically. And then we have an interpreter interpret that symbolic program. And if we just did while not at end of program, switch on macro assembler instruction, case 1, branch test object, case 2, branch test object shape, et cetera, et cetera, et cetera. Where any instruction could be followed by any other macro assembler instruction, that's like a huge explosion that will not solve in any reasonable time. So what we do is we take advantage of those first-class language constructs I talked about before. Cachet has the explicit static emit statements, as well as a symbolic label construct that when combined means that we can take the emit statements and trace out all the potential control flows between instructions that your code generator emits. So you get a structure of all possible programs that can come out of your stack of code generators. And then we take the interpreter and we effectively unroll it to match the structure. So it is an interpreter specialized to interpret just the programs that can come out of your code generators. So all control flow in all possible programs that come out of your thing is reified into actual control flow in Boogie. This also means that so this here is a lowering of the instance of instruction, which uses a loop to walk up the object's prototype chain until it finds one that matches. It's an unbounded loop, and we can totally handle that because the Corral solver says, oh, I see this is an unbounded loop structure. I'm going to apply my invariant inference and totally make that work for you. I don't have time to do this, but this is what the interpreter code looks like in Boogie. Evaluation is a work in progress. We've implemented 67 of the 333 cache ops currently that exist. I'm sure there'll be more tomorrow. That fixed slot generator I showed you verifies in 4 seconds. A version that handles just dynamic slots, it verifies in 39 seconds. Putting them both together, it verifies in 63 seconds. So we're not like blowing up as we add more branches to our code generator. We also did the unit testing stuff where we said, okay, here is, say, add, for example. We're going to take 2 symbolic numbers and we're going to plug them into the add instruction, make sure nothing blows up. And we did this for a bunch of different like code stub, not just per instruction, but like per kind of stub that can be produced. We took a stub from the browser and then we made it a symbolic version and we said test it. So we did all that. We did 27 of those so far. Median solving time is like 7 seconds. Minimum was like 0.53 seconds. Maximum is like 2 minutes. And that was something involving like simulating the stack and a call into the VM as well as floating point stuff. So solving time is pretty promising. We also did the translation validation thing I talked about before, where we run Firefox, dump out all the stubs it generates on speedometer benchmark. We got 159 stubs after deduplicating them because it generates a lot of duplicates. Supported by the ones that support all the instructions we ported over. There were 70 of those. Median verification time was 27 seconds. Minimum was 1.7 seconds. Like a couple of them were like 4 hours. Those were like an edge case they handled. It was like guard shape, load prototype, repeated like 30 times. We already have some optimizations working on to make that more tractable, but that was an edge case. Anyway, that's my talk. Yeah, cool. I didn't plan an ending, so that's it.
So, questions?
So I'm wondering, so what is the view for this, right? So you said at the beginning that the Spider Monkey developers are kind of already used to like adding a lot of assertions and everything. So do you think that, or maybe you already started talking with them, so will they pick this up?
Yeah, we've been sorry.
Development cycle.
Yeah, so like we work our lab, like we worked actively with Mozilla already in our like development process. Also, I used to work at Mozilla. Like this was designed like in communication with them and with their the workflow of engineering in mind. So yeah, we're like pretty. We're working with them, and ultimately, yes, we're very much working with the goal of like getting this actually landed in Firefox.
So like I don't know, whenever they commit something, you just run the verification and.
Yeah, there's already like a lot of CI infrastructure at Mozilla. In fact, they have their own bespoke CI system because their CI thing is so complicated. But I envision this personally as like a CI task that gets run like maybe every beta build or every release build or something, or maybe runs like a faster set of tests like every commit or something, and then like a slower one for release builds, things like that.
Okay, thanks. Super cool.
Someone else?
Yeah, maybe just to clarify, like, why exactly you needed to define your own language? Like, wouldn't have been possible to use something like Daphne or so?
Yeah, so there are two parts of that. One, we didn't want to use an existing language. Like we didn't want to parse C++ because like for C++ itself is a nightmare. But okay, maybe it was Rust. But like simulating the whole semantics for Rust or some reasonable language is like a bigger task than just being able to pick the semantics we want to simulate and do those. Then why not use existing research language like Daphne or something? This ultimately this needs to go into the back into the JIT engine, which it needs to be like high performance code that it can also handle like all the manual memory stuff that goes on outside of that. So garbage collection and things like that are a non-starter for us because you can't have your JIT run slow code because then there's no relatively slow code because then there's no point in doing the JIT in the first place. And as I said in one of the slides, having these like first-class features for compiler design gives our verifier, it forces the program into a structure that a verifier can work with to generate the stuff that can be verified efficiently.
Okay, I guess maybe we have time for one short question more. So if nobody else wants to, I'll go.
Okay.
And my question is, do you have some proof about the relation of the generated Boogie code and your Cachet programs?
You got me. Just by inspection, to at least address that initially, we're doing like having our code run versus having the original code run, doing unit testing as well as comparison testing between the outputs. But yeah, we don't ultimately, I guess ultimately the Cachet to Boogie versus Cachet to C++ thing matching is, at least for now, part of the trusted code base.
Okay, thank you. So let's thank the speaker again.